Hello and welcome to today's physics lecture, wherein we shall be discussing about this EM induction. Right from this lecture now we will be connecting the bridge between the EM induction and the devices for the alternating currents or the AC. Right? Previously we have looked on the Faraday's law, the Lenz's law and the eddy currents. Now we shall be discussing about the term inductance. Now for the inductance, the phenomenon that which is producing it is known as self-induction. So let us try to understand now that what is self-induction. Self-induction. Right? Now self-induction. To understand it better, let us draw a circuit diagram. Say for example, the circuit looks somewhat like this. Right? This is a normal inductor and this is the battery. This will be the positive side and this will be the negative side. Now if we do place a key as such, right? If we join the key, then the circuit will be closed. A current at that time will start to flow, right? If we join this key, then what will happen? The current shall be flowing like this. Right? This is the current, say I. Now as per Faraday's law, as per Lenz's law, the current that will be flowing over here, this will produce a magnetic flux, and due to the production of the magnetic flux, an induced EMF will occur, right? And the direction of that induced EMF will as such that it will oppose the change that is producing it. The change that is producing it will be in this direction. So, the direction of the opposing force or the direction of the opposing EMF precisely would be in this direction. Right? This entire scenario is during the make of a circuit. We are joining the circuit, we are closing it. So this is the scenario when the make of a circuit happens. So if we say that due to this opposing induced EMF, a current tries to flow, and say for example this is opposing, or we denote it as IO. The IO and the I will be opposing. So, in the case of the make of a circuit, IO will be in opposite direction, or IO is opposite to I, right? Now, for the next scenario, now if we want to break the circuit now, this is the normal inductor and this is the battery. The current was now flowing, and suddenly now we break this circuit, or the key is now open, right? So this is the scenario of break of a circuit. Right? Now, in this scenario, the induced EMF will say to this current, you are increasing, I will not let you increase, I will oppose you. And likewise, in this scenario, this opposing or any kind of this EMF that will be generated, it will say, oh my God, you are decreasing now, the current is decreasing now, I won't let you decrease, I will increase you. So in that direction, it will be over here. Because it is now decreasing, the current flowing through it is now decreasing, it will say, no, I would not let you decrease. So it will be in this direction. So over here, what we can say is that, if we say it I, O, or the opposite, in this scenario we could say that the EMF induced in the opposite direction or the opposing is opposite to the normal EMF, this one, and in this scenario we will thus say that the E of that is opposing for this kind of scenario will be in same direction to E. Right? And this is the reason why that if we make a circuit or if we break a circuit, the current, this current does not reach to its highest maximum value just the moment when it gets closed or when it gets joined, because there is an opposing induced EMF, right? So if we take, for example, this side as current and this side as the time, we will see there a graph like this. See, from the zero position, the current is now increasing, but it would not increase with a flash of an eye. Why? Because the opposing induced EMF will let it to increase at a slow speed, right? And afterwards, this is the scenario of the make of a circuit. This is for make of a circuit. Now afterwards, when the circuit will be break, the current will not reach over here directly at zero, because we can see over here that due to the induced EMF there will be a current flowing, so it will be likewise, okay? And this entire, the small scenario will be for the break of a circuit, right? So this is about the self-induction. Why self-induction? Because this opposing EMF in this coil or the opposing electric current due to this coil is only because of the current that is present within that particular coil, right? Some external effect is not coming into existence. So the self-induction may be defined as the phenomenon by which an induced EMF or current takes place in the coil due to the change of current in the coil itself. Right? Now it may be noted that this kind of things, this opposing thing will take place only in action during the make or break of a circuit. Otherwise, when there is a steady current, this kind of things will not take place, because it takes place in the coil only due to the change of current in the coil itself. So while during the make of a circuit, if the current was 0, now it is changing, so an induced EMF or the induced current will take place. Likewise, the I was flowing, now it is flowing down to 0. A change of this current is now taking place. A change of current in the coil is taking place, and that is the reason why an induced EMF or current will take place in the coil due to the change of current in the coil itself, which is known as the self-induction. Right? Now it is seen that the magnetic flux associated with this coil is directly proportional to the current flowing in the coil. So we can write this magnetic flux is directly proportional to the current which is flowing in this coil, right? And to change this proportionality into equality, we could take the help of a constant. So it will look like phi is equals to Li, where the phi is the magnetic flux, I here indicates the electric current present in the coil itself, and L now is known as the coefficient of self-induction, or is better known as self-inductance. So here this component L is known as self-inductance. Right? Now, taking this equation, if we differentiate both sides with respect to time, what we can get is d by dt component of phi will be equals to d by dt component of Li. Now this L will be a constant. It will depend on the material or something, but it is surely a constant, right? So we can write as d by dt component of phi will be equals to L of d by dt component of I, right? And previously from the Faraday's law and this Lenz's law, we were able to see that this d phi by dt, or the rate of change of flux with respect to time, we have seen it is equals to minus E, or this E was equals to minus of d phi by dt, where E is known as the induced EMF. Induced EMF in the coil itself now. So we can write this term, we can replace this term as minus E equals to L multiplied by di dt, right? So we can write it as E will be equals to minus of L di dt. This is the expression for the induced EMF, the self-inductance of that coil, and the rate of change of current in the coil itself. Okay? This I stands for this I. Okay? And this E is responsible for the making of I naught or IZO, or the opposite. Right? This is the case for over here also. So we have seen about the self-induction, about the self-inductance, right? Now we should look that whether the self-inductance has got any SI unit or not. Yes, obviously the self-inductance has got its SI unit and is known as Henry. Which is denoted by H. This is the SI unit of the self-inductance, right? Now, if this is the self-inductance Henry, we can also write that E equals to minus of L, where this d by dt component of I is equals to 1 or unity. Right? So, the self-inductance of a coil may be defined as the induced EMF of that coil provided or when the scenario if the rate of change of current with respect to time is unity, right? So this is about the self-induction. In the subsequent lecture, we shall be trying to understand the self-inductance of this, like a coil, a plain coil, a solenoid, and how we could minimize the self-induction, because we have seen that due to self-induction, the current is not getting at its peak value at a rapid rate, because this is taking this much amount of time, right? And also for the break, it is also taking this much amount of time. So the self-inductance actually leads to this time consumption for getting it up to the highest value or 0. So we shall be trying to understand that how we can reduce the self-inductance, and obviously what is the power associated with the self-inductance. Thank you.